All right, everyone. Welcome back to Chemistry 132B, Quantum Principles, Lecture 21. This is week number 9, and so we are entering the final stages of this course. We'll have, 3 more lectures this week, and we'll be talking about some last important topics. It's about molecular orbitals of pi conjugated systems, something that I hope you have some affinity with, and you may appreciate the methods that we will be discussing this week. And then next week, week number 10, which is the last week, we will not be introducing new material, but basically practicing the material we have covered throughout the quarter. So there's a lot of time for questions and practice problems and so forth, and I will walk you through a couple of key examples, questions that look like exam questions. So I will introduce the last part in this course this particular week, and just to kind of get back to what we did last week, because we had a midterm. Okay, we had a midterm on Friday. And most of you have completed that midterm. There's still a few people who have to do it, and that is why I will not be releasing the results and the answers until Wednesday. So if you ask me why it's not there yet, that is why. Okay, we still have a couple of people who have to do it, and so we have to wait for them to complete the test. So by Wednesday afternoon, everybody will have their score, and the answers to the questions will be posted as well. Okay. I'd like to reemphasize that I do have office hours every Friday at 1 o'clock. So if you have questions about the material, especially in these final stages of the course, please, join me for a session so you can ask your questions and see some examples worked out. All right, so I'm going to start with the new material today, and it has to do with things that we talked about last week, because before we started talking about the midterm, we were actually talking about the variation principle. Hopefully you remember that. The variation principle is a technique of approximating, a wave function. And so we were making trial wave functions and trying to find the best possible trial wave function by trying to solve a set of equations, which is called the secular equations. So the key principle there was, maybe you remember this, that we were trying to optimize the coefficients of the wave function, right? So we were making a linear superposition of 2 or 3 particular states, atomic orbitals. The coefficients need to be optimized, and the way we did that is by basically taking the derivative with respect to the coefficients and then finding those coefficients that give us the lowest possible energy for the ground state. That was a general guideline for us on how to find the lowest possible energy. And we did that. We saw that the variation principle gave us solutions for the energy E. And in the case of 2 atomic orbitals, we found 2 molecular orbitals, one with an energy lower, one with an energy higher, a bonding and an anti-bonding orbital. Okay, so that is basically what we did. So today we are going to talk about that as well, but in a slightly different context. Okay, because previously we didn't specify exactly what kind of orbitals we were talking about. So we talked vaguely about the hydrogen atom, where we have 2 s orbitals that overlap. Okay. But we didn't talk about more complicated systems. So there are, of course, more complicated systems, and one of them is shown over here. Here we see 2 carbon atoms that engage in 2 types of bonding. One is an on-axis sigma bond, and one is an off-axis pi bond. So how do we deal with that? Can we use the variation principle to learn about how to understand these bonds? And the answer is, of course, yes. But it's a little bit different than maybe what you expect. So what we're going to do is we are going to ignore, for now, the sigma bonds. Okay, so the sigma bonds are not the part that we will be focusing on. They are there, of course, but we will be focusing exclusively on the off-axis bonding, the pi bonding network. So we will be considering the specific case of pi conjugated molecules, molecules that have pi bonds in such a way that they are conjugated. Okay, so we'll start with the simplest possible example of that, and that is, of course, this particular molecule. There's only one pi bond here that we have to consider. So let's see if we can solve the molecular orbital for just the pi system, not the sigma bonds, but just the pi system, and see if we can learn something from it. Okay, so what we will expect is to find something like this. So we see that each carbon atom, let's call this carbon atom A. So the A state here is the p orbital from carbon atom 1, and this is carbon atom 2, which also has a p orbital. These two p orbitals can, of course, overlap and engage in a bonding and anti-bonding orbital. So we expect to see something like this. These are pi bonds, so pi, the bonding, and the anti-bonding, that's the pi star. Okay, so how can we use the variation principle to solve this problem and get some idea on how to find these energies? Well, the mechanism is very similar to what we've discussed last week. So we're going to make a molecular orbital, psi, which is a linear combination of the two atomic orbitals, A and B. And of course, we have these coefficients, coefficient Ca and coefficient Cb, that need to be found, or in other words, optimized, to find the ground state energy of this pi bonding system. Right? So that's what we can use the variation principle for. So using that mechanism, an analogy with what we did last time, we can find this kind of determinant. Okay, this is what we arrived at last time. This determinant, if you solve this determinant, you will find the energies E. Okay, so the E is in this determinant. And if you solve for this determinant, we can find the energies, solutions for the energy that should give us these two energetic states. So in this particular scenario, we can make some approximations that are very commonly made. And these approximations are called the Huckel approximations. The Huckel approximations are applicable to pi conjugated systems. Okay, so pi conjugated systems, we can make the so-called Huckel approximation. What are these approximations? Well, they're important because without these Huckel approximations, the problem becomes much more difficult to solve. Huckel says that S, which is the overlap integral, equals 0. So the S, of course, sits right there in the determinant. Okay, so we can say that that is going to be 0. That is interesting because that means that this whole term here is going to be gone. And that simplifies the mathematics here quite significantly. The second approximation is that all betas are 0. Okay, so the betas here are in the determinant as well. And they're all 0 except between nearest neighbors. What does that mean? Well, it's very simple. These two atoms here, atom 1 and 2, or A and B, are nearest neighbors. If there would be a third one that sits on this end right here, then that would not be a nearest neighbor of atom 1. So just imagine there is another atom here, right there, which is bonded to atom number 2. Then atom number 1 and atom number 3 are not nearest neighbors, so their beta is going to be 0. But the beta between nearest neighbors are not 0. They have a finite value. Okay, so that is also part of the Huckel approximation. And then finally, all remaining betas have the same value. So we do not discriminate between the beta between 1 and 2, and let's say 2 and 3, right? Because there's a beta between 2 and 3 as well. There's a beta between 1 and 2, and we say they have approximately the same value. So in a pi conjugated system, we can make such approximations. These approximations are not general. They are not general for the variation principle. They are specific to the Huckel approximation as applied to pi conjugated systems. Okay, so we'll take that, and then we're going to clean up this determinant here. All right, so with these approximations, we can really clean it up because, again, these ES's are going to be gone, and these two betas are going to be the same. So what we get is this determinant right here, alpha minus E. The E is the thing that we would like to solve for, okay? And so alpha minus E times alpha minus E minus beta times beta, okay? So and then you can reorder that. That's done over here. So what I'm doing after I just write this determinant out, I'm going to reorder and make these two terms to clean up the equation such that I can find my roots very easily. Okay, so if I write it in this particular way, you can immediately see what the roots are. Okay, and the two roots are E is either alpha plus beta or alpha minus beta. That is what we find right here. Okay, so you can see very nicely, if you write it in this way, you can see that E must be equal to alpha plus beta, E must be equal to alpha minus beta. Okay, so these are the two energies then, and this is exactly what we thought we would find using the variation principle, because we have, of course, E plus, which is alpha plus beta, and then we have alpha minus beta, which is the anti-bonding orbital. And the interesting thing is here that alpha, which is this energy of the individual p orbital. So alpha is the energy of the individual p orbitals, and beta is really the contribution that is either added or subtracted from it. Oops. So what I'm finding here is this level here is alpha. I go up by beta or down by beta. So beta is either added to the energy, and then I'm getting an energy that's higher because this value here is a negative value. Okay, so beta is negative, so that means that actually the energy goes up. And here, because beta is negative, the energy is going to go down, as you can see, right? Alpha is also negative, by the way. So these energies are all negative. The more negative they are, the lower they are. The less negative they are, the higher they are. So keep that in mind. Sometimes it's confusing, this negative or positive sign. But binding energies, remember, are always negative in general, right? So basically, I'm adding or subtracting a beta term from the unperturbed energies of the atomic orbitals, which are, of course, my p orbitals. Again, I'm not talking about sigmas. I'm not talking about s bonds from s orbitals, but I'm talking about pi bonds made from off-axis p orbitals. Okay, so this is what we find here. Now, this works really well. This works really well. This variation principle is applicable to this pi conjugated system, but things get quite difficult and complicated if we expand our pi conjugated system, because this is, of course, a very simple molecule. Only has 2 carbon atoms. What happens if we have 4 or 5 or 6 carbon atoms, like, for instance, benzene, which is a pi conjugated system, as we know? Then this variation principle gets quite complex, and the equations are pretty tricky to solve. So it will be helpful to have an alternative method in our pocket that we can use to solve problems of that kind. And that method exists, and is a very general method, which is kind of really the last method I'm introducing in this course. But it's a very important one. Maybe you'll recognize it. Maybe you've even used it in one of the courses so far. But we're going to derive it, and we're going to use it for this specific case of pi conjugated systems. Okay, so that the following couple of slides will basically go through that method, which is called matrix diagonalization. Okay, so here we have the general problem that we would like to solve. Here we have our Hamiltonian, okay? Here we have psi, which is the wave function that we'd like to find. E is the energy we'd like to find as well. The only thing that we have at the start of the problem is the Hamiltonian. I know what the Hamiltonian looks like. That's the Hamiltonian of my bond, okay? That includes all the charged particles that are participating in the bond. So what we've done is we have made an approximation for psi. Okay, we have said psi is a kind of a linear combination of states n, where n, these particular states, are now atomic orbitals. Okay, from different atoms. So this is not going to be a complete set, but it's still a linear combination of different states. So that is my trial function, so to speak. I'm going to put that into the Schrödinger equation and just see what I can do by just playing with this equation. Maybe I'm arriving at something interesting that I can use. That's what we're going to do. So we're going to put this way of writing the wave function into this, the general Schrödinger equation. And this is what I'm getting. Okay? I'm getting the H operating on this whole thing, but because Hamiltonian only operates on wave functions, I can basically move it over there. Okay, this E here is, of course, a constant, so that can stay on the left here. Don't have to do anything particular with it. So let's move this Hamiltonian in front of this particular wave function. So this is what I'm getting. H is operating on N. Now N, remember, is an atomic orbital. Okay, this atomic orbital is an unperturbed atomic orbital. So it's not an eigenstate of this Hamiltonian, because this Hamiltonian is the Hamiltonian of the new situation, which means the atom is now surrounded by other atoms, and therefore there's a lot more charged particles around it. Okay, it's a new situation that's not described by the wave function n. So this Hamiltonian, I don't know what happens if it operates onto this particular atomic orbital, because this is not an eigenstate. So I can't solve this right off the bat. I'm kind of stuck here. Okay. So what I'm going to do next, I'm going to multiply this whole equation, the one on the left and the one on the right, with a wave function m. Okay, m is also an atomic orbital. Okay, m is also an atomic orbital. So m is an orbital that is kind of similar to the orbitals that I'm making this wave function from. All right, so I can multiply it from the left with this bra. So now this Hamiltonian is sandwiched between state m and state n. And here I get this kind of overlap integral, as you can see, right? So what I'm going to do now is basically, I'm going to squint my eyes a little bit. I'm going to say, well, let's call this whole thing here, this integral right here that I need to solve, I call that HMN. Okay, that's the first thing I'm going to do. And then I'm going to say the following: m and n. Now, m is an atomic orbital, n is an atomic orbital. They're not necessarily part of a complete set. Okay, but if I'm pretending that the overlap integrals are always 0, which is what we've done in the Huckel approximation, remember, then I can say the only surviving term in this summation is the state Cm, because n must equal m in that case. That's the only one that's surviving. Okay, so in that case, I only have one coefficient left. So what I'm getting here is this equation. Now, that may not look like much, but actually it turns out this is a very powerful equation. So what I'm going to do next, I'm going to take this equation on the next slide. I'm going to fill it out for the case of our molecular orbital of the pi conjugated system. Okay, and then see what I'm getting. And then I'm going to make a more general statement about this particular equation. So here is what I'm going to do. I'm going to take what we've done already with the variation principle. I'm going to make a linear combination of two states, atomic state 1 and 2. These are two different atoms that are going to engage into a bond, a molecular orbital bond. Okay, so I'm going to fill out this psi in this particular equation. And you'll see how I do that. Because, of course, what I need to fill out here is the C1 and C2, because I see the coefficients in this equation. So those coefficients I'm going to fill out with coefficients C1 and C2, right? So there's two different ways to do that, because there's one sum here. It runs from n equals 1 to n equals 2, and then m can also have the values 1 and 2. So those are the possibilities. M is either 1 or 2, and n is also 1 and 2. N is a summation, but m is just a fixed value. So I have two cases here. When m equals 1, then I'm getting this equation. I just filled out this whole thing. This is the summation, so I get two terms. The first term is h11, because m equals 1 and n equals 1. And because n equals 1, we get C1 as well. And then the second term is when n equals 2. M is still 1, but n is now 2, so I get C2 here as well. M here is 1, so I get C1. So this is the first equation I'm generating by assuming that m equals 1. And I can rewrite this equation a little bit, like so. Okay, so I'm going to basically collect terms. This E is going to join forces with this H11, so I get H11 minus E times C1 plus H12 C2, that must equal 0. So this is my first equation I'm having right here. Second possibility is when m equals 2. Okay, so now again, just look what where these 2's and 1's come from. This 2 here, the first one, is m. Okay, now m is of course 2. That's what I just said. Okay, here's another m. That's all m. These are all m's. And n, that's this guy, is running from 1 to 2. So this is the first one, and this is when n equals 2. Okay, so this is the second equation I'm generating. I'm going to use this one and rewrite it in the same way as I did before, collecting terms in terms of the C2 and C1 coefficients. So this is what I'm getting. Then H21 times C1 plus H22 minus E times C2 equals 0. Okay, so I've generated basically 2 equations here. Now, what is the significance of this? You may wonder. Well, these 2 equations are very similar to the final result we arrived at with the variation principle, because these 2 equations I can write in the following way. Okay, I can write this in matrix format. You can verify that for yourself. This term right here multiplied by C1, this term H12 multiplied by C2. Okay, that generates the first line, and then the bottom line here of the matrix times this column vector will generate the second line. Okay, so this matrix way of writing basically regenerates these 2 equations. Okay, so basically this matrix represents the solutions of this particular problem. Now, you may recognize that this is just, if you want to solve this problem, you have to solve the determinant of this matrix right here, which is exactly what we have done for the variation principle. But I have to say that what we did here is not the variation principle. We didn't really optimize for the coefficients and then try to find the energies. Here, we started from the Schrödinger equation and tried to solve it in a very, very general way. Okay, so the bottom line from this exercise, hopefully you realize that we arrive at pretty much the same result as with the variation principle. We have to solve this matrix here, the determinant of this matrix, and that allows us to find the energies. Why is this a significant method? Because this method can be very easily expanded through larger matrices. Okay, so let me show you that. The equation here above, the main result that we derive, can be written in matrix form like this. Okay, you can verify it for yourself, where this H here, this big H, is the so-called Hamiltonian matrix. And for a wave function that contains only 2 terms, so for 2 atoms, that matrix looks like this. Okay, so it has elements, element 1, 1, element 1, 2, element 2, 1, and element 2, 2. So in this particular case, where I only have 2 atoms, it is a 2 by 2 matrix. The Hamiltonian matrix is a 2 by 2 matrix. What does the 1, 1 stand for? It stands for that the Hamiltonian operator is sandwiched between 2 states, 2 atomic states from atom number 1, right? And this guy here is the Hamiltonian sandwich between state 1 and state 2, where state 2 is the state of atom number 2. Okay, so that's basically analogous to what we've just done. Same definitions as the definitions used above. Now this C here is the so-called column vector matrix. What does it look like? It looks like this. I see a column vector CA and CB. What does that mean? Well, that means the following. This is the coefficients that belong to psi A, and this is the coefficient that belongs to psi B. What is psi B? Psi B is the second wave function that I can find in this problem. So think about psi A is the bonding, psi B is the anti-bonding wave function, right? Each wave function has two coefficients, as you can see, one here, one there. And therefore, CA has two contributions, right? Two coefficients, C1 of wave function A, C2 of wave function A. And the same for the antibonding. The antibonding has also two coefficients, right? C1 for the antibonding and C2 for the antibonding as well. So C, therefore, is basically a matrix composed of the columns here with the coefficients in them. All right, now E is a diagonal matrix with the energies on the diagonals. Okay, so what I can do now is I can rewrite this equation, and it's very important. This is a very important result. So I can multiply each side by the inverse of the column vector matrix. Okay, C -1, that's the inverse of the matrix. So if I multiply it here from the left, I get this term right here. But if I multiply this term by the left with C minus, then C minus times C equals 1. Okay, that's the unit matrix. So I get simply E. Now remember, E is a matrix with just the values of energy on the diagonal. So it's a diagonal matrix. H here is this guy right here, which is not a diagonal matrix. So this result says, very important, this result says that if I do this operation, meaning I'm multiplying this non-diagonal matrix by the inverse of the column vector from the left, and I multiply it from the right by the column vector again, that operation will produce a diagonal matrix where the elements on the diagonals are the energies that I am interested in. All right, now this is important because it gives me two things that I'd like to know in one operation. If I'm able to diagonalize the Hamiltonian, which is what this operation does, if I'm able to do that, then I retrieve two things. One, I have to find the column vector C. That's good, because if I find C, I have all the relevant coefficients of all the relevant wave functions that I'm interested in. Here, I only have two, because I only have two atomic orbitals, right? So I only find one bonding, one anti-bonding, but I find all the coefficients, and that means I have now access to all the wave functions in my problem. And secondarily, I also find the energies E. So I find what the energies are, and I find what the wave functions are by one operation. And the operation is diagonalizing the Hamiltonian matrix. Okay, so diagonalizing the Hamiltonian matrix produces the energy eigenvalues. This is what I would like to know. Of course, I'd like to know where the energies are. And they also give me the matrix elements of the column matrix C, okay? And that basically means that I have access to what my wave functions look like, what my bonding and anti-bonding orbital wave functions look like. Okay, so that's good news. It's a very powerful procedure. And so we will look at this from various angles, as you will see, and try to solve various important problems for pi conjugated systems using this method. So from now on, we'll not be using the variation principle, but using this mechanism to solve some important problems in chemistry. So just in general, I think you have all seen this, hopefully in your math classes and maybe in one of the lab courses of computational chemistry, that if you diagonalize a matrix, this is what you get. So in general, this is more general notation. You see here A, that is my, this is my original matrix A, which is not a diagonal matrix. So it has basically elements everywhere, okay? Then if I find P, where P is the matrix of eigenvectors, so those are the column vectors. So we wrote it as C, but P is the general way of writing it. And then if I take the inverse of this P and multiply A from the left, then this whole operation here is producing a diagonal matrix where on the diagonals I have the eigenvalues. Okay, so the eigenvalues of the newly diagonalized matrix are given right here. So it's a very general recipe. Actually, this recipe is not unique to quantum mechanics. It can be used in all kinds of problems, all kinds of physics problems. But here we use it for finding the new energies, assuming new forms of the wave functions. Okay, so let's do this for our particular case. All right, so here is the starting point. The starting point again is, we need to find C. H is something we can readily, compose. We don't have to do a lot of work to find H. And then multiply it from the left with C, and then we should be getting this new matrix, which has on its diagonal only values on its diagonal. So, and those values are the energies. So let's first look at what the Hamiltonian matrix looks like in the context of the Huckel approximation. So we're looking at the 2x2 system. We have two atoms that form a pi bond. And in that case, as we have already seen, H11, this is H11, is written as alpha. H12 is written as beta. H21 is the same beta. And then H22 is called alpha. Okay, so that's basically, we just give those matrix elements new names. But this will be helpful as we move along, as you will see. If we look at systems that are much larger than 2x2, then this alpha and beta notation is going to be very helpful. Now, these alpha and betas have nothing to do with spin states, right? Right? This is basically just a name for these matrix elements. That's what it is. Okay, what about those column vectors? So CA, that is basically the column vector. That is one column of the general matrix C. But this is not C itself. This is one column of C. It has two coefficients, because these are the coefficients of the wave function psi A, okay, the bonding orbital. We know what it looks like, because from the variation principle, we have solved this problem before. So I'm going to just take those examples. I'm going to just verify if this whole procedure actually works. So I know what psi A is. It's basically 1, 1, okay, where coefficients C1 and C2 are both equal to 1. That's simply the plus combination of the two atomic states. Now, the negative combination, of course, is in this particular case, it's called psi B. That means it's the second option that I can have, right? So in that case, the coefficient C1 is the same, it's 1, but C2 has a negative sign right now. Okay, so these are the two column vectors that belong to the two wave functions. The nomenclature is a little unfortunate here because this is an A, which sounds like antibonding. This is a B, it sounds like bonding. So that's a little unfortunate, but this is really my plus combination. This is my negative combination, okay? So what does C look like? Well, C looks like this then, because C are those two column vectors, and the matrix, if you make a matrix out of them, so it's CA and CB, then it looks like this. This is CA, okay? So the first column is CA, the second column is CB. This is how you make these column vector matrices. Okay, so we have now an expression for C. We know what C looks like, or should look like. So let's take this C, plug it in to this equation, and see if it actually produces a matrix that is diagonal with on its diagonals the values for E. Let's verify that. So what we have to do, we have to take the inverse of C, and how do you do that? In general, it can be quite difficult, especially for very large matrices. But for a 2x2, it's not so hard to compute. Okay, so here's a definition of a 2x2 inverse matrix. What you have to do is A, B, C, D. The inverse has D minus B minus C, and then A here at the bottom. And then you have to divide it by the determinant of this whole matrix. Okay? The determinant of A, of the original matrix, is a prefactor, and then the matrix elements are at different positions, and they have different signs. Okay, so but if you follow this recipe, you can find the matrix C. So as you will see, the inverse of C is given right here. So it's half, 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 minus half. Okay, so that is the inverse of matrix C. This one is C minus. This one is H, and this one is C itself. So now you have to do a matrix multiplication. You can do this by hand because it's a 2 by 2 matrix. So let's do that. First, you want to do alpha times 1, beta times 1, beta times 1, alpha times minus 1. So that gets rid of the 2 here and converts it into 1. And then you multiply it again with this matrix. All right? So what I'm getting is this. This is the outcome. Believe it or not, alpha plus beta, that's the first eigenvalue, the first energy, and then alpha minus beta, which is the second energy. Now, this column here, okay, this column right here, it belongs to psi A. So this is the energy of psi A, and that is the energy of psi B. Okay, which is nice because now I have basically the energies that belong to the wave functions that I started from. So what I'm finding is the energies are E equals alpha plus beta. That was for psi A. Psi A had the coefficient C1A, C2A, and they're given right here. They're both 1. Okay, so what I find here is simply state 1 plus state 2. That is my bonding orbital. It has the energy alpha plus beta. And then the other one has C1b, which is given right there, here. And then C2, comma b, which is this coefficient right here. That's a -1. Okay, so what I'm finding is 1, -1 here. That is the coefficient C2b. And then this atomic state 2. So atomic state 1 minus atomic state 2. So what I'm finding is that that's the state for the antibonding, and the energy that's associated with it is alpha minus beta. Okay, so what we've done here is we have tested this expression right here using the column vector matrix that I know is going to be the solution to my problem because we have solved this problem before with the variation principle. Okay, so what I've done so far is not really using this equation yet for solving a new problem. I'm just testing if this works in the first place. And what we've seen here is that yes, because these are the two energies we just found at the very beginning of this lecture with these two bonding and anti-bonding orbitals. Yes, there's a question about the determinant. The determinant is calculated in exactly the same way as we have done before for a 2 by 2. Okay, so there's an answer in the chat that is correct. It is A times D minus B times C. Okay, so that is basically how you calculate the determinant. All right, so this is basically what we are finding from both the variation principle and this new matrix diagonalization method. We find the same solution. Okay, that is, each carbon atom has an energy alpha because that is basically H11. This is also energy alpha because that is H22. Okay, and then if you form the molecular orbitals, I get two solutions: alpha plus beta and alpha minus beta. Remember, these are negatives. Okay, so that's why when you see a negative here, you don't go down, you go up. All right, same here. Plus means not that you go up, but you go down because beta is a negative value, as is alpha. So the lowest state is the bonding state. We know the coefficients. That is coefficient 1. It's coefficient 1 here too. So that is the bonding combination. The antibonding has a 1 here and a -1 right there. So that is the antibonding combination, right? Just as we saw with the variation principle, it's the same here in this new method. So what we find, go up by beta, go down by beta, and these are my two states. This is the pi ungerade and pi gerade, which is the antibonding one. Okay, so this is the general recipe. And what we'll do on Wednesday, we're going to use this new method, matrix diagonalization, to solve problems that are a little bit more challenging than the problem of this simple molecule where you only have 2 carbons that contribute to the pi conjugated system. We're going to look at systems that have 3, 4, 5, and 6 atoms that contribute to the pi conjugated system, and you will see that that's really hard to solve with the variation principle, but relatively straightforward with this matrix diagonalization method. And it will allow us to understand the energy states in molecules like, for instance, benzene or cyclobutadiene, for instance. Okay, so that's up for Wednesday. This was by means of introduction of the diagonalization method. Okay, folks, that's all for today. A little early, but that's good. We got plenty of things to do today. Let me know if there's any questions about this material or any questions about the midterm that we had in terms of logistics or administrative issues. Just let me know. There's a question about when the grades will be posted for midterm 2. As I said at the beginning of the lecture, they will be posted on Wednesday afternoon. There's still a few people who have to do the midterm. That's why we cannot post it now. You have to wait till everybody has completed the midterm. So Wednesday afternoon.